Seema Jaggi Madam. Madam is Assistant Director General in ICR New Delhi. Madam has contributed immensely to the science of statistics. She has guided 13 PhD and 10 MSc students and published widely in international journals of high influence. She is the fellow of NAS Punjab Rao Deshmukh Outstanding Women Scientist Award of ICR, INSA Teacher Award, Best Teacher Award of ICR, and many more. We are extremely happy that she has spared her valuable time today. Thank you, madam, for accepting our invitation. And now I request Dr. Seema Jaggi madam to enlighten us about the today's topic, that is inferential statistics, testing of hypothesis and ANOVA. Thank you, madam.
Thank you. Thank you, Dr. Arora. Thank you so much. And good morning to each one of you. And first of all, let me convey from my side thanks to the organizers, especially Dr. Gopal Arora ji, for giving me this opportunity. Actually, my subject is statistics, but now since I am now in more towards the administration side, so teaching side now it has reduced now. But anyhow, I make it a point that in these type of training programs, I try to deliver. And whatever little bit I know in the subject of statistics, I think that I should pass it on to the others. Whatever knowledge or whatever I have learned over the years, I would like to just deliver it in today's talk. So first of all, I would like to just share my slides. Is it visible?
Yes, ma'am, it is visible.
Oh, good. Thank you. Now slideshow also, no?
Yes, madam.
Yes. So the topic for today is inferential statistics, right? You all have I think for the last 10 days, you have been studying statistics. So now I think some of you are from the statistics background, but many more are from the non-statistics background. So we have started with the very basics of statistics. Maybe you had the class on the collection of data and then the descriptive statistics and graphical procedures and so on. So then another branch. So what I thought was initially, because my lecture was scheduled on 7th, but I'm sorry I could not deliver on that day because of my other engagement. So I just thought of first telling you basics about that, which I can skip. What is statistics? This is now very clear to you. For the last 10 days, you have been hearing this. The main thing is your data. The data is your different types of data which you have. You can broadly classify it into the qualitative data and the quantitative data. And you have different procedures, different statistical procedures are there depending on what data you have. So accordingly, you apply the statistical procedures or the statistical tools which are available. So under the qualitative data, you may have the nominal data, which you call it as a categorical categories, like male, female and all that. That is nominal data. And then there is an ordinal data where you can rank or place the data in an order, in an increasing order or a decreasing order, or so order. So that is your qualitative data. And when you come to the quantitative data classify into interval and ratio, right? So interval is the one where your data is in the form of interval, and the zero, the difference between these two is in the ratio, the zero is also observed. The zero means null, whereas in interval, zero means some value in that, like your temperature. So 0 degree is a value in that. So this is the difference. But normally, whatever quantitative data we have is normally in the ratio scale. So like in the agriculture, if we go, the yield is there, or some other survey, we go height, weight, all these are all ratio levels of the measurements. Further, your data could be a survey data or an experimental data. So why I showed this slide was to tell you that depending on what type of data you have, accordingly you decide what technique to be used for the analysis, right? Changing. Okay. So the applications of statistics, where it applies in all fields, starting from marketing, from finance, industry, human resource, psychology, social science, agriculture, medicine, everywhere you have the application of statistics. Wherever data is there, you have the application of statistics there. Maybe it depends how do you apply it into different fields. The technique remains the same. The statistical technique is the same. The descriptive statistics, you have the same technique. How do you apply it? Only that it changes as per the field in which you are applying it. Right? So broadly, we classify statistics into two parts. One is your descriptive statistics, other part is the inferential statistics. Right? The descriptive statistics, which is already covered with you, gives you a summary of the data. Means it summarizes, give maybe in the form of some numeric figure or in the form of some graphical procedure. It just gives you a summary of the entire data. It could be the mean, it could be any other measures of central tendency are there, the variability measures are there. So all this will just describe your data. So under descriptive statistics, you have this all classification, distribution, the graphical procedures, the central tendency, variation, measures of variability. All these fall under the descriptive statistics. Just you have a data set saying that this data has this mean or this data has this variance, it has this much standard deviation and so on. Now, the other part of the statistics is your inferential statistics, right? Inferential statistics is basically drawing inference out of the sample data which you have, right? Suppose you conduct a survey and you get the observations from each and every unit in the sample. Now, from that survey data, you work out some descriptive statistics from the survey data. Now, say you find out the mean. Now you want to know whether whatever I have obtained from this survey data, whether it holds for the population or not. Population is a bigger one and survey is a part of the population. So whatever you obtain from the sample, that is a part of the population, whether it holds true for the population also. So that is drawing inference about the population from a sample is a inferential statistics. Right? So under the inferential statistics, you have the estimation procedures. How do you estimate? Whenever you want to estimate means, what do you want to estimate? We always want to estimate the population parameters. And how do we estimate? Based on the survey data. You have a population, suppose, of 1,000 units. Out of that, you cannot enumerate all the units. So you take a survey sample, say sample of 100 units. Based on those 100 units, you want to estimate some characteristic about the population. What is the mean height in this population, or what is the mean yield in the overall good? So there are different estimation procedures available. The second part is the testing of hypothesis. Testing of hypothesis, which is the main thing which we'll be dealing today. That means from the population, you have again taken a sample, and then from the sample, you have obtained some statistics. Statistic means some function of the sample values. Now, based on that function of this, which you have obtained from the sample, now you want to draw certain inference about the population. That is your inferential statistics. That means drawing inference about the bigger one from a smaller one. Right? So now in this under descriptive statistics, as I told you, this is just a summary of the entire descriptive statistics which we have. Right? Summary measures. You have central tendency, you have variation. Under central tendency, you have mean, median, mode. This is already done, I think. This I can skip also. And then in the under variation, you have variance, standard deviation, range, coefficient of variation. And besides this, we have some other measures which are called as partition values. That is your quartiles, percentiles, deciles, quintiles. These are all describing your data. Right? These measures help to describe your data. The slides are not changing, it's very slow. And see, this is describing the shape of the data. Again, the variability. So if seeing this, suppose you plot your data and you get it something like this. So what is the first one showing? The middle one is showing that your data is symmetric because your all mean, median, mode are same. That means the middle figure, that is your mean, median, mode, the data is equally distributed towards the left and towards the right. So that is your symmetric data. This one shows that it is more tilted towards the left side. This is the left skewed data and this is a right skewed data. Now I come to the actual topic, which is your testing of hypothesis. Now, why do we require it? Just few situations I have mentioned here on testing of hypothesis, and then we may go for one by one just situation. Suppose you want to compare the effectiveness of different methods of teaching. Like one teaching is which we are doing now, the online teaching. Other is the blackboard teaching. Some is say some other methods of teaching. Distance learning is there, and so many things are. I want to compare the effectiveness. So how do I do that? If statistically I want to compare it, so what I will do is I will take some data points from the students who are in the classrooms, from the students who are in the distance learning, and from the students who are going for this type of online teaching. So then based on that data, I will try to compare based on the different statistical procedures, which one is the best or whether all of them are at par. Suppose I want to know the average yield of a crop in a district. Again, I will use this test. I want to compare two varieties of a wheat with regard to their mean yield. Or I want to assess the water quality in terms of salinity levels, which is affecting the fish body metabolism. So again, I will use this test. Suppose I want to find if some new drug has come up in the market, and I want to know its effectiveness, whether it is really effective for a particular ailment as compared to the existing drug which is available in the market. Same way, if suppose I want to know whether average self-confidence score of college students is equal to some specific value. Or if I want to know the intelligence level measured through intelligence quotient, is it up to some standard? Or to compare the effects of stress management programs on self-esteem. Or I want to know the mean hourly pay rate of men is same as women or is it higher? Or to compare two processes with regard to production of certain items. These are few objectives which I have listed. Again, it will depend on what work you are doing. Accordingly, you frame your hypothesis and you do the further data collection and you do the analysis. So what are tests of significance? So a statistical test, it is a procedure. There are certain rules, certain steps which you have to follow, which helps you to take a decision about a hypothesis. And hypothesis is always about the population, right? Based on that hypothesis, what you have about the population, you try to verify that theory or that hypothesis based on your sample data. So here we have parameter. Whenever I would use the word parameter, parameter is always about the population, right? And the word you see statistic, it is not statistics. This is singular statistic. This is about everything, whatever you have about the sample. This is about sample and this is about the population. And then we come to the statistical hypothesis. What is a hypothesis? So like we represent it by H naught, null hypothesis and alternate hypothesis, right? So hypothesis is a statement about the population. As I told you, hypothesis is always about the population. You should never mention anything about the sample in your hypothesis. It's always about the population. It may be a statement, it may be a number, say mean height is equal to 165 centimeter. That is my hypothesis. I want to test that hypothesis, right? So their hypothesis could be simple or it could be composite. Simple means mean height is equal to 100. That is simple, exact value. Composite means mean height is greater than 165. You're not sure, so you're giving a greater than or not equal to or less than, this type of symbol. So it becomes a composite hypothesis, right? So the null hypothesis, the hypothesis which you are testing or which is under the test So that is based on your sample data is your null hypothesis. But null hypothesis is always, again, I am emphasizing, it is always about the population. Alternate hypothesis is, suppose I have taken here null hypothesis mean, mu represents my population mean. So mu is equal to some specific value mu naught. This is a simple hypothesis. And alternate could be either mu is not equal to mu naught, less than mu naught, or greater than. These are all composite hypothesis. This is simple, this is composite. But at a point of time, you will take only one null and one alternate, either of these. So when it is not equal to, we call it as a two-tailed test. You're not sure whether it is greater than or it is less. So we call it as a two-tailed test. Whenever it is less than this, we call it, these two are single-tailed tests. And among this is called as your left-tailed and this is your right-tailed test. Right? So this is how you call your null hypothesis and your alternate hypothesis. Then another important term which is very used in this testing of hypothesis is your level of significance. So how much of level of significance means how much of the error you can accommodate. See, no data is error-free. There is always some proportion of error involved in there. That error could be of any type. So how much of error you are able to accommodate in your data, that is your level of significance. That means, so if suppose I say 5% level of significance, so that means out of 100 cases, I can go wrong in 5 cases. That is where I will reject my null hypothesis, which should have not been rejected, I am rejecting it. So I'm taking a wrong decision. So that is why we do not go beyond at a very high level of significance. We go up till maximum 5. In agriculture situation, what we here apply is maximum of 5% level of significance. But in certain situations, you may go little higher also, but not beyond 10%. That much of error, suppose you can accommodate in your study. So these are some terms which are very often used in your testing of hypothesis. That is why I'm describing you these terms. The test statistic is any function of the sample value. Based on your sample data, whatever you work out, say mean, sample mean. Sample mean is a statistic. And then based on that, you work out certain formula that is called as your test statistic. And then other term is your critical value. The critical value for a hypothesis is a value to which the value of the test statistics is compared. This is the test statistics. From here you will get some value, and critical value is the value with which you will compare the statistic. Accordingly, you will draw the conclusions, right? So if you see here, I'm showing you here one graph that is your data, which is a bell-shaped curve, asymmetric data. And if you see here, this part and this part, this is the critical value, 1.96 and minus 1.96. So I will compare my calculated value, which I get from the here, with this 1.96 and minus 1.96. So this is at 5% level. So if my value is coming, calculated value is coming somewhere here in between, this is called as your acceptance region. And if the calculated value falls either here in the shaded portion or here, these are the rejection regions. So if my calculated value falls here, we will say my hypothesis is rejected. Same way, if it falls here, it is rejected. If it falls somewhere here, we'll say it is not rejected. Right? So it is always compared with the critical value. And here is the critical value. For 5% level of significance, my critical value is 1.96 or this side minus 1.96. Okay. So the step for testing is, first step one is setting up the hypothesis, both null as well as the alternate. Step 2 is what test procedure. I'll be describing some of the test procedures. So which test to be used? And based on that, you have to calculate the statistic. Suppose I am using the t-test, so I have to use the test statistic accordingly calculated. Then the test criteria, that means whether you are rejecting it or not rejecting it. That is step 3. And based on if you are rejecting, what is the inference? If you are not rejecting, what is the inference? That is your step 4. This holds for every test. These 4 steps have to be followed. Now, the different types of tests are there. We can classify into 2 forms. In the first slide, I showed you the type of data. So depending on the type of data, if your data is quantitative mostly, like ratio or interval, we go for these parametric tests. Parametric tests, all these are, except this chi-square, falls under both categories. For some situation, it is parametric. For some, it is non-parametric. But otherwise, this normal F, they're all calculated based on the quantitative data, okay? Either interval or ratio. Whereas the other set of procedures, which are called as non-parametric tests, these are mostly for the qualitative data, ordered data, nominal data if you have. So that is it. These are a series of non-parametric tests are also there, like Kruskal-Wallis test is there, Kolmogorov-Smirnov test is there, Wolfowitz test is there. These are all non-parametric tests, which normally we use when our data is either in the nominal form, that is categorical form, or ordinal form, that is, it is in some order also, or it is in the form of codes, right? So I'll be covering the parametric test here. So first test is normal test based on these tests are all 2-3 tests I'll be telling you based on the normal distribution, that is normal test. So the first test is testing the mean. This is the most popular thing which we are normally testing, mean of a population. Mu is equal to mu naught. This can also be written in this form. The sample has been drawn from the population with mean mu naught. Both things mean the same, just this is a way of writing it. So this is my null hypothesis and this is my alternate, any one of them. Either I take two-tailed or I take single tail, left tail or right tail. To select only one. So all this requires that the data which I have or the data which I am collecting, the survey data, it is drawn from a normal population. Because all these parametric tests, whatever are there, they are all having a strong assumption of normality. Because these tests are derived based on the assumption that our population is normal. So we draw a sample which I represent by xi, a sample of size small n is taken from a normal population, right? So my test statistic here becomes x bar is my sample mean, mu is my population mean. What I'm testing is the mu, that is the population mean. So my test statistic here becomes z. Normal test is represented by z. So z is equal to sample mean minus population mean. This is what I want to test. How much is the deviation, or whether whatever I get from the sample, it is truly representing the population or not. So this is the deviation between the sample mean and the population mean divided by the standard error. That is sigma divided by root over. It is the standard error of mean, which is sigma upon root n. We know n is the sample size. So all these things, if it is your sigma is, suppose your population variance is known. So your sigma is also known. X bar you are calculating from the sample, mu is from the population, and accordingly I apply this test and do it. Suppose if sigma is not known, then I can estimate it from the sample variance. This is population variance, we can estimate it from the sample variance, right? So now in this case, since it is a normal test, there are certain defined critical values. You can see critical value, I told you, no, that it is the value by which you can compare the statistic with the critical value, right? And if your test statistic falls beyond critical value, then it is rejected, and if it is less than the critical value, it is not rejected. So this for 5, suppose for 5%, I showed you 1.96 is the critical value for a two-tailed test. Same way, 1.64 is the critical value for a single-tailed test. So these are some critical values. Normally, we use either 1% or 5%. So you see here one example I am showing you. Here there are 6 randomly selected farmers' data. What is their total income in thousands? Like this is 6,700 is the income of, so these are 36 farmers, right? So I have collected the data from 36 farmers. Now I want to know, can it be concluded that the average annual income of a farmer in a particular village is more than 7,000? Based on this data, I want to infer about the entire village. So what, you know that sample size is 36. Now, since here your sigma square is not given, I have estimated it from this 36 points, the sample variance, which is 2.27. Now, my null hypothesis, I'm taking that we should normally try to keep the null hypothesis as simple. So this is mu is equal to 7,000. That is the average income of a farmer is 7,000. And alternate, I keep it as more than 7,000. I've taken a single tail test. So I apply here the Z formula. This is X bar. X bar is the mean which I obtained from this 36. Then this is mu, which I have taken in the null hypothesis, divided by sigma, is I have estimated 2.27 divided by root over n, that is 36 value. This value comes out to be 2.11. Now you see, since this is a single-tailed test, I will see only on one side. If it is two-tailed, we see towards both sides. So since it is single-tailed, you see on one side. This 1.64 is the critical value at 1% for 5% single-tailed. Same way 2.33, as I showed you in the last table, 2.33 is the critical value at 5%, as I showed here. See. This is at 1.645 is at 5% and 2.33 is at 1%. Same thing I have showed here. Now your calculated value which we have got is 2.11. So 2.11 will fall somewhere here. So what do we infer from here? We infer that if we take at 1% critical value is 1.64. So if we take at 1%, my hypothesis, since it is falling in this shaded region, it is rejected. Right? So at 1% level of significance, we are asked to test at 1% only. So at 1% level of significance, my hypothesis is rejected, and we conclude that the average is not rejected, sorry. At 1% it is 2.33. At 1% it is 2.33, you see here. So since it is lying outside this 2.33, so at 1% it is not rejected. Had I compared it at 5%, that is 1.64, then it would have been rejected. But at 1%, since it is not falling in the shaded region, my hypothesis is not rejected. And we conclude that the average income of the farmers in that particular village is, on an average, it is 7,000. Right? Same way, one more example I've taken here for this. Again, from a class, 36 students were selected at random, and their marks in a subject out of 20 were observed. I have not given here the data. The mean and standard deviation are calculated here this way, 18.7. Test whether the mean marks of the students is 19. So we have 36 students. So my null hypothesis is mu is equal to 19. And alternate, I have taken two-tailed. Mu is not equal to 19. Since it is two-tailed, that is why both sides I am showing you the shades. So X bar is given as 18.7. N is 36. Mu is we have taken as 19. Sigma is given here as 1.25. Just club into the Z formula, and I get minus 1.440. So what do I see here? That at 5%, at 1%, 2.58, I showed you, here 2.58 is the value at 1% two-tailed. 1% two-tailed is 2.58. So you see here 2.58 on this side or minus 2.58 on this side, right? So my value is minus 1.44, where minus 1.44 will lie somewhere here. So it is coming in the acceptance region. It is not in the rejection region. So we say that null hypothesis is not rejected. Hence, we conclude that the mean marks of students in a class is 90. Okay. What is important is how do you infer and how do you see where my value is lying. Through this graph, it is very clear that my value is lying in the acceptance region. If it lies somewhere here or here, we say it is in the rejection region. Now, same way, that was for testing only single mean. Suppose I want to compare the marks of students in a class separately. I want to compare the marks of girl students with the boy students. So I want to compare two different, I want to compare the means, different means. So that means I have two different populations. The population of males, and other is the population of females. Take a sample from the males, which is of size N1, and sample mean X1 bar. From the females, I take a sample of size N2 and X2 bar. And I want to compare that. Please. Yes, any question? Okay, fine. So we will have the questions in the end. You just note it down so we can discuss in the end. So mu1 is equal to mu2. This is what we want to compare, the equality of two means. So that way also we can do here this. Instead of X bar, now we are having difference of sample means minus difference of population means divided by the root over standard deviation. So this is the formula for equality of two means. Something I have applied here. I think I have one more. No, this only. I have two sets of samples and one of size. I have not given you a data because data is big. This is 42, this is 32. I have the sample mean and so on. And we have just applied here the test of equality and we obtained the Z value as 3.36 and 3.36. If you see that it is greater than 1.96, that is at 5%. So H0 is not accepted. And we say this is the two sets of data with respect to the average expenditure per month per family in the two populations. So it is not equal, right? Now the same way we can test for single proportion. Proportion means out of, suppose in a class, out of 30, 25 have passed and 5 have failed. So what is the proportion of students who have failed is 5 by 30. So if suppose you want to test certain proportions, that way in that case also you can use this Z test. That is, you have a sample of size and out of this X possess a certain characteristic. Say number of students passed or number of seeds. I have sown these many seeds, but this many have germinated. So the proportion of seeds germinated, that is the proportion. So X by N is my proportion. And P, capital P is my population proportion, which I want to test. So testing the hypothesis will be population proportion P is equal to some value P naught. And alternate could be any one of this. So my Z statistic becomes small p minus capital P divided by PQ by N. Okay. So I've taken here one example. In order to test the conjecture of the management that 60% employees favor new bonus scheme, a sample of 150 employees was taken. 55 employees favored the new bonus scheme. This based on this, what is my proportion who have favored is 55 by 150, which is 0.367. And I say that my conjecture is or my hypothesis is that 60% of employees have favored it. This is my hypothesis. So I've taken H0 as P is equal to 0.6. 60% means 0.6. And alternate is not equal to. So just plug in into this my sample proportion, which is 0.367 minus population proportion divided by PQ upon N. So I get this value as minus 5.825. And at the 1% level of significance, see if you see this value is higher than this, my H0 is rejected since it is falling in the rejection region. And that is why we conclude that since it is rejected means that concluded that 60% employees do not favor the. My hypothesis was it is 60%, but my hypothesis has come out to be wrong. So 60% are not favoring the new bonus scheme. Same way, like we have equality of two means, same way we have equality of two proportions also. We have two different populations and we are drawing samples from two different populations and trying to equate the this. We have P1 and P2 as the sample proportions from two different populations, and these are the population proportions, capital P1 and P2. And my null hypothesis, I want to compare equality of proportion. Suppose you take this example. In a village, 50 farmers out of 80 farmers with large land holding and 78 farmers out of 250 farmers of small land holding adopted a new variety of wheat. So what is the proportion of farmers who in the large land holding is 50 by 80, and in the small land holding it is 78 by 250. So is there a significant difference in the adoption of variety? Well, I want to test that the proportion of farmers who have adopted a variety in large land holding and small land holding, their proportion is same or not. So thus I have taken the null hypothesis that it is same. So 50 by 80 is my first sample proportion, 78 by 250 is my second sample proportion, and just I apply this formula and I get the value as 5.085, and at 5% level of significance, the value is 2.58. My null hypothesis is that my calculated is more than the significant value, so it is rejected, and we say that the adoption rate is not the same. It is more in which, wherever the proportion is more, it is more in the land holding, large land holding farmers, which is 0.625. Even though you can see a difference is clear, but we have to test it statistically, considering all how many farmers are there, what is the proportion is there, then we have to draw the conclusion. Okay. Now I come to the second set of tests, which are t-tests. Normal test, I have already told you, single mean, equality of two means, single proportion, equality of two proportion. Now I come to the t-test. In this also, the first test is single mean only. Now what is the difference? Say, and the next test will be equality of two means. But when do we go for t-test and when do we go for normal test, right? See, important thing is when our population variance is not known, then that is one important point, when your population variance is not known. The second important point is it is a small sample. If your population variance is known, whatever be the sample size, whether it is small or big, we will always go for z-test. But when your population variance is unknown and your sample size is small, then we go for this t-test, right? Again, we have the same thing. We want to test single mean, and my t statistic is, instead of z, now I am writing here t, which is sample mean minus population mean divided by this SYS, because sample variance is not known. So we substituted by the sample population variance is not known. So we put here the sample variance and accordingly this, right? Now here this will always follow a t distribution. We have separate t in the literature. There are t distribution, there is f distribution, chi-square distribution, and so on. These distributions are available, which have been derived from the normal only. So when I come to t, there is another concept coming here, is degrees of freedom. So t with n minus 1 degrees of freedom. Degrees of freedom means how much of freedom I have in selecting the observation. For example, I tell you, suppose I want to select 10 data points from some individuals, and I have fixed that my mean is fixed. Out of the 10 points, mean should be, say, mean will be 2.5. So I will go on selecting. First one I can select randomly, second I can select randomly, until 9 I can go randomly. But the last observation gets fixed. Why? Because my mean is fixed. So I have put one restriction on that. So that because of that restriction, my freedom of choosing all 10 points is not there. It is only I can select 9. So my degrees of freedom will be 9. So that is why we have kept here n minus 1 degrees of freedom. One example of this, suppose a claim has been made that the height of adult males in a college is different from what it used to be, and we wish to test this hypothesis. A campus-wide survey made 20 years ago found that mean height of males was 69.5 inches. To study this, a random sample of 15 males of the same age from current students was taken and their height recorded. So these are the heights of 15 males, right? So it is in inches, it is given. The average height is 69 point. I want to test whether the height is same, which it used to be 20 years ago. The average height, which is 69.5. So my null hypothesis is 69.5 inches. Now, based on this 15 data points, my mean is coming out to be 70.4 bar. And S is 0.71. Just substitute here, since the sample size is small, variance is not known, I'm applying here t-test. So 70.4 is my sample mean minus the population mean divided by sigma s upon root over n, which is this value. This comes out to be 1.27. And t will be 14 degrees of freedom. Now we will compare this calculated value 1.27 with the table value. Separate tables are available. Like for normal also, I have given only 2-3 values. We have table for normal. Same way we have tables for t, tables for f, tables for z, f, chi-square. All the tables are available. So again, I will show you. See, this is the table for t. One side you have degrees of freedom and other side you have level of significance. So suppose I want to test, this is tested at say 2.14 value of t at 5% and 14 degrees of freedom. 5% and 14 degrees of freedom is 2.14. You can see here this value. This 14 degrees of freedom and 5%, 2.54. So I'm comparing it with that. So value of 2.14. And since this calculated value is less than, so that means it is falling in the acceptance region. So my hypothesis is not rejected. So we say that the average height is 69.5 inch, what it used to be 20 years ago. Another example is there, based on field experiment, a new variety of green gram is expected to give a yield of 12 quintals per hectare. The variety was tested on 10 randomly selected farmers' field. New variety has come up and it is we have shown it on 10 farmers' field. And we want to see whether its yield is 12 quintals per hectare or not. So this is the yield from the 10 farmers' field. These are 10 figure data points. So my null hypothesis is that the average yield is 12 quintal per hectare. Just apply X bar, we get it from here. S also I get it from here. And then this is the sample mean, this is the population mean. The value comes out to be 1.86. We'll compare it with the t table value at 9 degrees of freedom. So at 9 degrees of freedom, the value is 2.262. 2.26. This is the value. So since this calculated value is again less than the table value, it's not rejected. It is under the acceptance region. So we say that the mean yield of the new variety of green gram is 12 quintal per hectare. Okay. Even though you see the variations are there, in some farmers field yield is 14.3, in some it is 10.9. But on an average we are talking, so on an average the mean yield is 12 quintal per hectare. This is the t table. Same way we can do it for equality of two means. Like I did it for single mean. Same way we have equality of two means, like we did in Z test. Same. Only population variances are unknown, and we assume that we have two populations. Their variances are unknown, and we assume the population variances are also equal. So T is difference in sample mean minus difference in population mean, which is we are assuming equal, so that part goes off, divided by this. There are two populations. One is we are having a sample of size n1, so degrees of freedom will be n1 minus 1. The other population is sample is n2, so degrees of freedom will be n2 minus 1, and we add it n1 plus n2 minus 2. So that is what is the degrees of freedom. It is n1 plus n2 minus 2 degrees of freedom. That is what we have obtained here. So this is one example of two means. In order to compare the effectiveness of two sources of nitrogen, you know that nitrogen either you can obtain namely from the ammonium chloride, other one is from the urea. These are the two sources of nitrogen, ammonium chloride and urea. So we have applied these two sources of nitrogen to say these are I think 12 plots. 1, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12 plots. To 12 plots we applied ammonium chloride. To another 12 plots we applied urea. want to know which source of nitrogen is better or both are same. Whether you apply ammonium chloride or you applied urea, you will get the same yield. So these are your yield figures. These are from the 12 plots where ammonium chloride, and these are from the 12 plots where urea is applied. So this is the null hypothesis that applying both is, again, I'm saying we always keep null hypothesis simple. That is equality sign. So both the means are same. Whether you apply ammonium chloride or you applied urea, your mean yield will be the same. So we apply this. X1 bar is the mean of these figures. X2 bar is the mean of these figures. And then we find the sample mean from here, sample mean from here, and we club it, and we get this t value as 0.1865. And then degrees of freedom will be n1 plus n2 minus 2. That is 12 plus 12 minus 2 is 22 degrees of freedom. So we see the table value at 5% and 22 degrees of freedom is 2.074. Right? I think here 12 degrees of freedom, it will come out to be here. Okay. So from this you can see that both the, since calculated value is less than the table value, so we conclude that both the sources of nitrogen have similar effect on the grain yield. Whether you apply ammonium chloride or you apply urea, both will have the same effect. That is the yield in both the cases. Average yield in both the cases will be same. Now, which one to use? That will depend on other factors like suppose which one is, they say the price, the cost. Which one is cheaper? You will try to use that particular source of nitrogen. Another example in this, in order to compare the reading ability of a dyslexic children by placing a blue, dyslexic children have some problem in reading. So a technique was used by placing a blue plastic overlay on reading material. And this is blue overlay and this is a clear overlay. And this is the reading score which has been obtained from the students. 12 we have here, students, 12 we have here, different students. These are 12 and these are 12. Assess whether reading ability of these children improved by placing a blue plastic overlay. It is assumed that by placing this blue overlay, the reading ability of the student, those who are suffering from this particular ailment, may increase. So that is what we have to see. We are assuming both are same and we apply the same. We have the sample mean for both and we get the value as 4.15. Again at 12 plus 12 plus 22 degrees of freedom. If we compare this, so what do we get is the calculated value is more as compared to the table value. And this is a single-tailed test. Why? Because it is our assumption that by placing blue overlay, your reading ability will increase. So this is greater than this we have taken. Thus, the blue plastic overlays on reading ability material improves visual processing and provides immediate improvement in the reading ability of dyslexic children. I have tried to take examples from different fields wherever, again, depending on what your area is, you can. So the next important test is your paired t-test. Paired t-test is when the same set of samples are taken at 2 points. The data on set of, right? This test is also called as before-after test, right? So in this case, your sample will be n pairs of values. And here what we do is we try to see how much is the deviation before and after, how much is the deviation, which is called as your DI. But again, the aim is mean before and mean after, whether it remains same or not. So particular example, I will give you a very example. So my T will be this is deviation mean divided by S upon root. Right? So example, this is a clear example. In a study to know the effect of training to 8 researchers on a particular subject, following are the pre and post training scores. Suppose in your case also, when this training was started on 1st of June, suppose some exam would have been taken. And then after your training is completed, again an exam is taken. So you have these scores. So we can see whether after more or less similar type of question, not exactly the same. Similar type of questions are asked. And then we want to conclude whether after the training is completed, the mean score has increased or not. Right? So that is your before and after test. Same, I have taken here one example. Before training, this was the score. And after training, this was the score. So can we conclude that training has improved the performance of the researchers? These are same set of persons, or the 8 persons which were observed before and the 8 persons after they were observed. So mean before is equal to mean after. That is what is my null hypothesis. And alternate I am taking because I am very sure that training will improve the performance. So mean before is less than mean after, or I can write mean after is greater than mean before. So this is my single tail test. So this is the before score, this is the after score, this is the deviation. So then the deviation mean I can take, and this is the t-value, 4.32, and at 7 degrees of freedom. So my t-value at 7 degrees of freedom is 1.90, and the calculated value is 4.32. So calculated value is very higher as compared to the significant value 1.90. So the null hypothesis is not accepted. We say that since it is not accepted means the mean before and mean after is not the same, and we have taken that the mean after is more than the mean before. So training has improved the performance of the researchers. Right? So this is what is called as your paired test. Normally this test is applied whenever you want to study some impact, suppose impact of a technology. Some technology is developed and it is passed on to the farmers, right? And farmers are using it. So before they were using that technology, what was their income? And after the use of that technology, what is their income? If you want to test that. So you can use this paired test. You can take the data from those sample data from the farmers before the technology, after the use of technology, and you can study the impact of that particular technology. Okay? Now I come to the chi-square test, another set of tests which are called as chi-square. Still now, whatever test we were doing was testing the mean. And this is the test used for testing the variance. Right? Sigma square is equal to sigma naught square. So this is one test, and this is the test statistic. So here, whenever we are using the variance, again, I have to draw a sample from the population which is following normal distribution. And there are always 2 parameters of the normal, mean and variance. Earlier, we have tested mean, assuming either variance is known or unknown, so on. Now we are testing variance, assuming mean known or mean unknown. If mean is known, we use this. That is, the statistic remains the same, only the degrees of freedom becomes here. Because if it is known, it will remain n. If it is unknown, we have to estimate it, so n minus 1 degrees of freedom. Rest, the formula remains the same here. Instead of mean, since it is known, we put here mean. If it is not known, we put substituted by the sample. This is an example of the chi-square test. I think, skip this. Now, the another important test of chi-square is testing the goodness of it. Goodness of it means there is some theoretical result available. And then there is some theoretically practical thing which you are doing. You are obtaining the data. Now you want to test that whatever I have obtained through my experiment or through my observation, whether it fits to the theory or not. That is my goodness of fit. Theoretical and practical, how much is the deviation or is it same? That is my goodness of fit test. Okay? So here, what do? This is all based on numbers, frequencies. That is why this is a non-parametric test. For this purpose, chi-square is a non-parametric test. For testing the earlier one, variance, it is a parametric. For testing goodness of it, it is a non-parametric test. Right? So this is a number, observed frequency, and then we have the observed frequencies actually which you get from your study. Expected frequency is what you get from the theory, which is available in the books or in the papers. And I want to see how much is the deviation in this. So observed minus expected whole square divided by S. This is my chi-square statistic, which is based on the frequencies or based on the numbers. Again, I will show you an example example and it will be clear. I will tell a genome always have nucleotides. So in nucleotides, there are 4 types of nucleotide: A, T, G, C. Adenine, I mean, those who are from the life sciences or other background, they know it has 4 nucleotides: adenine, thymine, guanine, and cytosine, A, T, G, C. So suppose I want to know whether in a particular sequence, the frequency of these 4 nucleotides is same or not. That is one aim where I can use this test. Suppose the hypothesis to be tested is the nucleotides of a particular sequence have equal probability. So the data which I have in the sequence, A is coming 410 times, C is coming this many times, G is coming this time, and T is coming this time. But I want to study my null hypothesis is that all are equal. All the frequency of all these nucleotides is same. So if the frequency of all these nucleotides is same, means there are 4 nucleotides, so all of them are 25%, 25%, 25%, 20. That means 1 by 4, 1 by 4, 1 by 4, right? All has to be same. But if you see from the observation point of view, we are getting this. So this is the observation, and this is the probability of each of them coming. So since there are total, N is how much? This total is 21. Total nucleotides are 216s. Out of this 216s, A is 410. So 2166 divided by 4, if I take the number, actually which I should get. This figure is 2166 divided by 4 is 541. So theoretically, all these should be 541, 541, 541, 541. Theoretically, equal, if I say equal frequency. But practically, you have got this. So the observed minus expected whole square divided by expected, I do it for all, and I get this as the calculated value of chi-square. And the table value of chi-square, there are 4 classes, so 3 degrees of freedom is 7.1. This is very small as compared to the calculated value. So my null hypothesis is not accepted, it is rejected, and we say that the nucleotides of this particular sequence do not occur with equal probability. So always have maybe C is more, always in every nucleotide, C will be more, and in every sequence, C will be more as compared to this or this. This is the inference. Same way you can apply this. Suppose there are 4 different brands of apple juice in the market. And these 4 brands of apple juice, I say that they are equally preferred by the consumers. So if I want to test that, equally preferred means all will have the proportion of 1 by 4, 1 by 4, 1 by 4. So there are 4 brands. So in order to test that, suppose I take 100 individuals were randomly selected and they were asked to give their preference. My null hypothesis is all will be 1 by 4, 1 by 4, 1 by 4, which is 0.25. So they were asked the preference. So 20 individuals, they said brand A as their first choice. 31 said brand B. 28 said brand C as their first choice. And 21 said brand D as their first choice. Right? This is the choice which I have observed from the 100. Whereas if Harry sees all of them should be 25, 25. 25 should prefer A, 25 should prefer B, C, and D. This should be the actual value. But we have got this. How much is the deviation? And then observed minus expected whole square divided by expected. So this way we can see that our calculated value is less as compared to the table value. So my hypothesis is not rejected, it is accepted. So we say that yes, all the 4 brands of apple juice are equally preferred. It is 25%, 25%. Even though there is a deviation, but on an average, if you see, all are equally preferred. This is the chi-square table. Right? Another test for chi-square is testing the independence of attributes. Suppose you have 2 attributes, say age or education and income. These are 2 attributes. So I want to see whether the income is related to education or not, or whether income is independent of education. So I want to test this independence. So again, I use the chi-square test. So here you place the 2 attributes in the form of a table, which you call it as a contingency table, 2A table. Here you suppose A1, A2, A3 is my income levels, 10,000, 10,000 to 20,000, more than 20,000. And here is the education level, say metric, graduate, postgraduate, and so. And this will be your numbers. How many observed numbers? That is the number of persons whose age is, whose income is, whose education is this, and whose income is this. So this is all your observed frequencies. So again, you do observed minus expected. Expected also we find out through the formula, that is, what do you do is we get a total here which is called as row totals, and we get the total here which are called as column totals. So the expected for this will be row total multiplied by column total divided by grand total. That will give me the expected for this. So same way you can find the expected value for all. And we apply this formula and accordingly we do it. Here we have one example. This is a contingency table of order 2 by 4. One side, technology adopted or not adopted. And here is the educational standard of the farmers, illiterate, metric, graduate, and postgraduate. And this is the number. There are 60 farmers who are illiterate and they have adopted a technology. Here there are 25 postgraduate farmers who have adopted the technology. Right? So this way I want to test whether educational standard has any impact on the adoptability of innovation. So my null hypothesis is always that these two are independent. Adoptability is independent of educational standard. I found out the expected value. These are the observed. Expected is, suppose I want to find the expected for this particular cell. So this row total multiplied by this column total divided by grand total will give me 110.2. So this way we have obtained all, and observed minus expected whole square divided by expected. So my calculated value is 96.99. Table value is 7.82. So calculated is much higher than the table. So hypothesis is not significant, and we reject it. And we say that the adoptability of farmers is, we are rejecting it. It is not independent. It depends on the educational standard. Adoptability of a technology depends on the educational standard. Right? Now, another set of tests which are called as F test. Right? We have done the normal test, T test, chi-square test, now the F test. This is the test for the comparison of two population variances. For single variance, we have done chi-square test. For quality of two variances, we use this F test. Again, we have two different samples from two different populations, N1, N2, X1 bar, X2 bar. And just we want to test the null hypothesis that the variances of the two populations are same. We just take the F statistic is nothing but the ratio of the two population variance. So this follows a F distribution with N1. F will always have two types of degrees of freedom. So N1 minus 1 and N2 minus 1. So we have, suppose we have two different samples, sample A and sample B. I want to test whether this variation in this is same as the variation in this. So my sigma 1 square is equal to sigma 2 square, and I just take the ratio F as S1 square is the variance of this divided by variance of this, which I get to be this. So I will see the F table at 5 and 4 degrees of freedom and then compare. The value at 5 and 4 degrees of freedom is 5.19. So 5.19 is this calculated is less than the table. So my hypothesis is not significant and I'm not going to reject it. So we say the two samples have the same variability. The two samples are drawn from the population which has the same variability, right? This is the F table. Now I come to the another important test, which will lead towards the ANOVA, now analysis of variance, coming to the other part of this. Suppose till what it did in normal was testing the single mean or equality of two means. T-test also we did the same thing, single mean and equality of two means. Suppose I want to test equality of more than two means at a time. Mu1 equal to mu2 equal to mu3 equal to I have 5 populations and I want to test that. For example, suppose the effect of 5 different chemicals is to be tested. So for this, what we have done is we have suppose 20 units of solution are taken and assigned one chemical to 4 units each. right? There are 5 chemicals. Each chemical is given to 4 units. So that means 5 into 4 is 20 units we have. Now interest is to find out whether the effect of these 5 chemicals on the solution is significantly different or not. What do we have to test? We have to test that the mean. What do you want to test? Effect may be in terms of, suppose you are testing the growth of a virus in that. So how much is the growth? That is your observation. So I say that the 4 units where chemical 1 is applied, another 4 units where chemical 2 is applied. So mean of 1 is same as mean of 2 is same as mean of 3, 4 and 5. So 5 different means have to be tested here. So how do we do that? We cannot apply t-test. We can apply t-test, but we will have to test 2 by 2 at a time. Suppose in one go I have to test that. So here is the concept. So here is the concept which we use, that is your analysis of variance. Just see here the analysis of variance concept. The same example, chemical 1 is given to 4 units, chemical 2 is given to 4 units, 3, 4 and 5. And these are the observations, right? Maybe it is growth of a particular virus. So what do you see here? Here you got the value as 2.5 and here you got the value of 2.8. So why this difference is there? This difference clearly you can see that because here chemical 1 is given, so this value is there, here chemical 2 is given, so this value is there. So this is clearly, we can say that because 2 different chemicals were given, so this 2 difference in observation is because of that. This is called as between variation, between the chemical. Now if you see this 2, here also there is a difference. Even though the same chemical is given, still there is a difference. Why this difference is there? You do not know the reason for that. There may be some extraneous factors, some environmental factors may be there because of which this difference is coming. So this is called as within variation. Within the chemical variation, this is the between the chemicals variation. So what is the concept of ANOVA? Concept of analysis of variance is, even though you are testing the means, your null hypothesis is you will test the equality of means, but you will do it through the variation. So your total variation, you see, you have got here 20 observations. So 20 observations, you have one variance. So that is your total variation. That you can divide it into 2 parts. One is due to some known cause. You know why this variation is there, like this. You know why this variation is there because 2 different chemicals are given. So that is your known cause of variation. Another part is unknown cause, which is your this one within. You do not know the reason for this. So that is your unknown cause of variation. So this known cause of variation is, in this case, is your chemical. Or whatever treatment you give, that is the known cause. Here, unknown cause you do not know. That constitutes your error. So what do we do in this analysis of variance? So analysis of variance is a systematic procedure of partitioning or decomposing the overall variation into different components, a known cause as well as unknown cause. And your null hypothesis is you are comparing the means, but you are doing it using the ANOVA, and ANOVA uses the
मीटिंग की आवाज खोल दो, अनम्यूट करो, कर दिया, मीटिंग लीव करो.
Hello.
Yes, ma'am. We are
Right.
listening.
Okay. So the F statistics, I told you, it is always the ratio of 2 variances. So what is the variation between the sample divided by variation within the sample? I showed you, no? This variation divided by this variation is your F value. And through this, you can test whether your null hypothesis of equality of the 5 chemicals, whether their mean effect is same or not. This is the concept of analysis of variance, right? So I will take the same example which I showed you here. I want to perform the analysis of variance in this case. The same data points I have taken here, 20 data points are there. In first 4, chemical 1, then chemical 2 and so on. And what is my null hypothesis here? I want to test whether the mean by giving chemical 1, mean virus growth is by chemical 1 is same as mean virus growth by applying chemical 2, so on till 5. So I find out the between variation. So between group variation is between chemicals, and then within variation I try to find out that is within group. So this is you can see the structure of an analysis of variance table, in which the first column is always what is the source of variation. So in this case, you have one source of variation is chemical between, and the other source of variation is within. So within part is your actually the error part. Within groups will constitute your error. So there are 5 groups. So we have 4. The second column is the degrees of freedom. So 4 degrees of freedom. Total there are 20 observations. So 19 degrees of freedom. Remaining 19 minus 4 becomes your error degrees of freedom. The next column is your sum of squares. That means you have 5 groups. You have to find the sum of squares between these 5 groups. Sum of square, you know, xi observation minus the mean of this group whole square divided by n, that is 4. So this way you find the sum of squares. This is between groups. This is within group, the sum of square. Then mean square is nothing but the sum of square divided by degrees of freedom. This is actually nothing. Mean square is nothing but your variance. So variance within the group, between group, and variance within group. And F is the ratio of between divided by within. This total means what? The total variation. Total variation is partitioned into between groups and within groups. And when you compare this F value, you get this value to be 14. And in the table, the F value is 5.85 for 4 and 15 degrees of freedom. The value is 5.85. Since your value is much higher, the calculated value is much higher than the table, our null hypothesis is significant. Significant means we are going to reject it. And hence the mean values of 5 chemicals are significantly different. And through ANOVA, you have now tested that the mean of 5 chemical treatments are significantly different, right? At one go. But I cannot say that all the 5 are different. It is on a whole, it is different. Rest, maybe mean 1 and 2 are same. For that, you have to again go for some further tests. But ANOVA will give you overall that this is that significant, whether there's a significant difference among these groups or not. Now, this is called as, since you know only one source of variation, known source of variation. So it's a one-way ANOVA. The dimension of the ANOVA depends on how many sources of variation you know. Since here you know only one source of variation, that is chemical. So it is besides error and total, you have only one source of variation. So you call it as one-way ANOVA, right? Then suppose in this, the first 2 observations were collected in day 1. And the next 2 observations were collected on day 2 in all these chemicals. So if there is a variation between 2.5 and 2.8, I say it is because of the 2 chemicals which are applied. Now this difference may be because now difference between 2.5 and 2.2 I have to see. It may be because this is day 1 and this is day 2. Between 2.5 and 2.1, it is not known because same chemical, same day. So that is your error part. So now one more source of variation you have been able to identify, which is your day. So now ANOVA, in ANOVA, you will have one is variation due to chemicals, other is variation due to day. So chemical is 4 degrees of freedom. Day we have observed on 2 days, so 1 degree of freedom. Total will remain the same, 19. Error is 4. But one more source of variation you have been able to identify. You will find the sum of square for that also, mean square. And now you will compare. There will be 2 F values. One is comparing F chemical with error and day with error. So you are getting here 2 F values. And here you are getting whether it is significant or not. This is also significant. This is also significant. This I have obtained from some software. And they are giving here significant value. Both are less than 5%. So this is also significant. So that means here I am comparing two hypotheses. One is mu1 equal to mu2 equal to mu3, mu4, mu5 with respect to chemicals. The second one is mu1 equal to mu3, mu2 with respect to 2 days. So two hypotheses are being tested. So it is a two-way ANOVA. Both of them are significant. So that means there is a significant difference among the chemicals, and also there is a significant difference among the days. So the more you know about the sources of variation in your data set, the better result you will get. So this is a two-way ANOVA. Suppose you have been able to identify one more source of variation, it will become a three-way ANOVA. So this way we have multi-dimensional ANOVA. Right? One example I have taken here from the other field, that is a reading specialist wishes to compare how first grade students in her school respond to 3 new reading programs. There are some reading programs are there, and what she does is the teacher, she makes 3 groups, and to group 1 there are 5 students, group 2 there are 5 students, and group 3 there are 4 students, and there are total 14 students. And to first group, 1 reading program is given, to second group, 1 reading program, and this is the reading score which has been obtained. Maybe some procedure has been applied. Now, what is the aim? Null hypothesis is the mean of group 1 is equal to mean of group 2 is equal to mean of group 3. So here there is only difference between 7 and 12 is because they are from the two different reading programs are given to them. Between groups variation are there, but between groups we do not know. Maybe I do not know about the students which have been selected here, whether they are of the same age group. If they are of the same age group, still the difference is coming, then it is a clear part. If you can further classify that they are from the different age group, you can have another source of variation also. But right now, we are having only one source of variation, which is the reading program, different reading programs. So between groups, there are 2. Total, there are 14. So 13 degrees of freedom. The remaining goes to the within group, that is 11. Sum of square, mean square is calculated. Then this value is this 90 divided by 1.64 is 54. And the table value is 19.4. So my calculated value is larger than the table value. So the hypothesis is significant and is going to be rejected. So we say that hence the mean score of 3 groups are significantly different. So this is what we have concluded. I think this is my last slide which I wanted to share. Yes. So thank you very much. So this is all what I wanted to share with you all. So ANOVA is applicable. Further, there is so many dimensions of ANOVA. Then if you want to, depending on how many data points you have, if you want to study some interactions, whether there is an interaction between this and that can also come as a part of the ANOVA. Right? This is simple. I have shown you one-way ANOVA and a two-way ANOVA. Right? Simple. Thank you very much. Thank you.
Thank you, madam. Now I request all the participants, if you have any query, you can ask in the chat box.
No, you can ask directly also, no problem. Anyone, if you want to ask anything? In chat there.
Hello.
Yes. Chat box, no query is there, only thank you is there. And any question?
Thank you so much, ma'am.
My pleasure, my pleasure. But you have my email, you can note down my email, any query, any related to this or any other statistical thing, advice or anything required, guidance required, you all are most welcome. I hope I have been able to deliver what I wanted to say. Yes.
Yes, madam, you have covered all the topics related to the testing of hypothesis, and the main thing is that you have explained this with different examples that touches every discipline, psychology, even basic sciences and agriculture. The way of presentation is very nicely explain all the things. Thank you, madam.
Thank you.
And Thank you, madam, for making us understand about inferential statistics, testing of hypotheses and various tests, ANOVA, one-way ANOVA, two-way ANOVA, with different examples that touches all disciplines, psychology, basic and applied sciences, agriculture, and also big thanks to the whole FDP team for being there to support IT team. Thank you very much. Thanks to all wonderful participants. Thank you.
Thank you. Thank you so much. Thank you. Again, I say my email address and everything is available. For any advice, any guidance, any support required from the statistical point of view, you all are most welcome. Thank you.